In this lesson, we'll talk about complex number systems. The complex number system arises from the fact that sometimes when you solve a quadratic equation, or degrees higher than quadratic, you sometimes run into pieces where you cannot find a real solution. However, it is practical to sometimes try to find a way to write the solution anyway, which we'll talk about momentarily. What we're going to do is we're going to define this unit I, as I is the square root of -1. We know you can't take the square root of a negative number. So what we're doing is we're defining a new unit, which is not a real number, and we're going to use it in solving equations. One thing to note is that you also have the equation I squared equals -1. Also, if you have any other negative number inside of a square root, we just define it as I times the square root of the positive number. And if we were to square that, we would get just -a in the same technique. Let's start out with some examples. This is, because it's negative, I times the square root of 9. Now we know that the square root of 9 is 3, so often we'll write it in front as 3i. Next, same kind of technique. This would be I times the square root of 12. And we know that the square root of 12 is really square root of 4 times 3. So I can factor out the 4 and get 2. So a lot of times I write this 2i times the square root of 3. Now officially the correct way to write it is 2 square root of 3 times I. But the reason that I don't usually write it this way is because this I cannot be inside the square root. And students in general don't really pay attention to the fact that where their square root ends is very important. Where the square root ends is where the inside of the square root is done, and I has to be outside the square root. So to avoid confusion, we'll often put the I right in front of the square root if there is one. Next is for us to calculate a few powers of I, just to see if we understand how it works. -I squared. Let's simply write out what that means. That's -I times -I. Now we know that a negative times a negative is a positive, and that still applies here. So we get just positive I squared, which is -1. I squared is -1, as is negative I squared. Next, we've got I cubed and I to the 4th. Well, let's do it the way that it might make sense. I cubed would be I squared times I. So if I squared is -1, that's -1 times I, which would be -I. So I cubed is -I. And then I to the 4th. Well, that would be I cubed times I. We just said that I cubed is -I. So if we multiply these together, we get -I times I, which is -I squared. Again, I squared is -1, so we get +1. This is an interesting point. I to the 4th is +1. And I think it makes sense that I squared is -1, and so if you square it again, you get +1, and I to the 4th would be I squared squared. We can use the fact that I to the 4th is 1 to do much higher powers. Basically what happens is it cycles. It cycles between 1 and -1. And if you go 1 power at a time, it goes powers, go I, -1, -I, +1, I, -1, -I, +1. And it just repeats like that. So it's kind of easy to take care of higher powers if we can just figure out how to use the repetition to our advantage. You'll notice that it repeats every 4. So here's the technique that we use. What we're going to do is basically take 42 divided by 4 and only pay attention to the remainder. So 4 goes into 4 one time, and then 4 goes into 2 0 times, and we're left with a remainder of 2. What this means is if we're writing I 42 times, we're just going through this list. 1, 2, 3, 4. 1, 2, 3, 4. And so 40 of these things will go by, and we'll just be repeating ourselves, 40 being this part right here. So the remainder is all that remains. All I'm really getting is this repeating cycle, and so what I can do is say this is equal to I squared. All you have to do is keep the remainder, and we get that that's negative 1. Let's do 79. Let me write this over here. Again, you divide by 4 to figure out, well, what is the remainder? 4 goes into 7 one time. So we have 3, and then 39. 4 goes into 39 9 times. And so we have a remainder of 3. So the remainder of 3 means that this is equivalent to I cubed. That's what the cycle is doing. I cubed, we know from above, is negative I. And there you have it. So to do higher powers, all you have to do is divide by 4 so that you can figure out what the remainder is. All the other 4's disappear. Let me write one little formality here just to see it. What's really going on is I'm writing it like this. 79 is 4 times 19 plus 3. That's what we really just found by doing the division algorithm. So this is how I'm going to write it. This is I to the 4th to the 19th power times I cubed. Well, I to the 4th is 1, as we know. And 1 to the 19th power times I cubed, well, 1 to the 19th power is just 1. So as you can see, it really is equivalent to I cubed. But in general, we can just assume that whatever the remainder is when we divide by 4 is the only power that matters because of this cyclic nature of powers of I. Let's talk about the complex number system. What we want to do is be able to do operations on these. If we take some real numbers a and b, and we put them together as a plus bi, we call this a complex number. Complex numbers are an even larger set than the real numbers. The real numbers are a portion of the complex numbers. We often denote it with this C, and written on the board, this is usually how it's written, just one vertical bar. All the real numbers can be paired up to create the complex numbers. So you get two real numbers making up one complex number. A is called the real part of the complex number, and B is called the imaginary part of the complex number. Notice that I didn't say BI is the imaginary part. We're really just paying attention to coefficients. Notice that if B were equal to 0, then this part would be gone, wouldn't it? And so we just get a real number. And if A were equal to 0, then we would just get this, which we call purely imaginary. There's no real part at all, just a real number times I. Complex numbers, though they seem like we're just coming up with this stuff, I mean, who works with a square root of a negative number? Believe it or not, they actually do arise in solutions to real-life problems. And when they do, it turns out that complex numbers are very similar to sines and cosines. Let's continue on with the concept of operations. To add, subtract, and multiply, what we do is basically treat this like any other polynomial expression. And in the case of multiplication, if we run across an I squared, we change that to -1 to simplify our answer. And if need be, you might also run into higher powers than I squared also. Your goal is to get everything in terms of just I. No powers of I whatsoever. So the first one, 2 minus 3i plus -1 plus 5i. All I really did was dropped my parentheses, which is fine for addition. 2 plus -1 is 1. -3i plus 5i would be 2i. Think of it as -3x plus 5x if you want. Next example. Again with subtraction, I distribute my negative sign. So I get +1 minus 5i, and then just combine it again. 2 plus 1 is 3. Negative 3i minus 5i would be negative 8i. And we're finished already. So addition and subtraction is pretty simple. Now let's look at a multiplication problem or two. So let's use FOIL. First, negative 2, outer, 10i, inner, positive 3i, and last would be negative 15i squared. Now remember, if you have powers of I, you need to deal with those before you finish your answer. We can get a 13i by combining like terms. And remember, I squared is equal to negative 1. So we really get negative 2 plus 13i plus 15. And then negative 2 plus 15 is 13. So 13 plus 13i is our solution. Next one. Now if you'd like, you could write this out as 2 minus 3i times 2 minus 3i and FOIL. But I'm going to use the shortcut from the last lesson. First number squared plus twice the product plus the last number squared. And again, it doesn't matter with the negative sign there because we're squaring it. So I end up with 4. 2 times 2 is 4 times negative 3 is negative 12i plus 9i squared. So remembering that I squared is negative 1, this is really 4 minus 12i minus 9. And so I get negative 5 minus 12i. Next idea. This is something that we're going to need in order to handle division of complex numbers. So to divide complex numbers, we need something called the complex conjugate. Complex conjugate is simply take this middle sign and switch it. If it's positive, make it negative. If it's negative, make it positive. Complex conjugates are very nice in that when you multiply them together, because you've got this difference of squares property going on, you come up with a real number. So let's just multiply this out directly and see what comes up. First, outer, inner, and I'll rearrange as ABI. Last, negative B squared, I squared. Notice that these two terms cancel out. And then I squared is negative 1 again. So this really just becomes plus B squared. There's no i's in this. This is a real number. So if we want to divide complex numbers, we can use conjugates to get a real number in the denominator. By getting a real number in the denominator, we can knock out any i's in the denominator. You'll also notice that I got a nice formula. You can totally use this formula to help you rapidly compute what comes out when you multiply a conjugate together. Let's move to a division problem. So here's the technique. In order to get rid of this complex number in the denominator, you'll multiply by its conjugate. So 2 minus 2i becomes 2 plus 2i. And we'll do the same thing in the numerator. So now what we do is we FOIL these out. First, 2. Outer, 2i. Inner, negative 6i. And last, negative 6i squared. In the denominator, you can either FOIL it, or you can be smarter than that and use the formula that we just got. I'll FOIL it over here. 2 minus 2i times 2 plus 2i will be 4 plus 4i minus 4i minus 4i squared. Well, just like last time, these cancel out, and I get 4 minus 4 and then an I squared. Since I squared is negative 1, that makes it a plus 4. and so I get 8. But remember, you can just use the formula a squared plus b squared. You can use the shortcut. 2 squared plus 2 squared. So if I clean this up, I get 2 minus 4i. And remember, when you got an I squared, it becomes a negative 1. So I really get 6. And the denominator is now just 8. So let's come over here. 2 plus 6 is 8. And this is an answer we get. Now, I actually don't like this answer. Once you get to a problem like this, what you really should do is simplify it a little bit further by splitting up your fraction. So divide both of them by 8. And now you see, as my final answer, I get 1 minus 1/2 I. And that is the most ideal form of the answer. The next problem is for you to try. Feel free to pause your video and resume it whenever you're finished. Okay, hopefully this problem went well for you. So if not, just feel free to pause if you ever figure out what to do to fix your work. I start out with 1 plus 4i in the denominator, so I need to multiply by the conjugate. Remember, what I do to the bottom, I need to also do to the top. I change the plus to a minus, and I do the same thing on top. So for this part, I get 2 minus 8i minus I plus 4i squared. And in the denominator, again, we'll take our shortcut. 1 squared plus 4 squared. Remember, it's always a plus in between, even if the number's negative, just like we had in the previous problem. So I get 2 minus 9i, and then the 4i squared becomes a negative 4. 1 plus 16 is 17. So I get negative 2 minus 9i over 17. We'll do the same thing as we did last time and write this as negative 2 over 17 minus 9 over 17i. And since these don't reduce at all, that's our final answer. Last problem. Now this one looks a little bit strange because it's just an I in the denominator. If you wanted to, you could just multiply top and bottom by I and be done. But let's be a little bit more clever than that. The conjugate of I, if you think of it like 0 plus I, would be 0 minus I. So what I'm going to do is multiply top and bottom by negative I. If I multiply top and bottom by negative I, I'm really multiplying by the conjugate. The calculation's pretty simple for the first term. I get negative 2i minus 3i squared. And on the denominator, you could use the conjugate trick here, a squared plus b squared, but this time I think I'll just multiply it out. I get negative I squared. So in the numerator, I get negative 2i now plus 3. And remember, I squared is negative 1, so negative I squared is positive 1. So division by 1, it can just go away. And I really get negative 2i plus 3. But I'm going to write it as 3 minus 2i. So that problem's pretty quick as long as you think of, oh, why don't I multiply top and bottom by negative I?